Hello everyone, I'm Chris McIntosh. I help teach the statistics courses. This week we're talking about multiple regression. These, the information for this lecture comes from chapter 12 of the Navarro text. You read the Heavey text on regression last week, and you can skim it again. It never hurts to go over the same information. And Heavey does talk about multiple regression, but the sections for multiple regression, most of this comes from Navarro. So just to review, correlation allows you to quantify the strength and direction of a relationship. You have two continuous variables. To make predictions, we need to know more than just the relationship between the variables. We need to also know the y-intercept. And last week we talked a little about the equation for a line. Y equals mx plus b is what we all learn in the United States. The equation is similar for outside of the US. And then we use basically that same equation, but we write it a little differently. And we say that y hat, which is the predicted value of y, is equal to b naught or b0, which is the intercept, plus b1x, which is b1 is the slope. In multiple regression, we can have more than one predictor variable. So the additional predictor variables are added to the equation using numbered subscripts. So in this case, if we had a multiple regression that had three predictor variables, we would write that as y hat is equal to b naught plus b1x1 plus b2x2 plus b3x3. And each independent variable will just get another bx with a subscript after them. Multiple regression minimizes the distance between regression line and data to estimate. So we saw this illustration last week with the line through the middle of the data on the left, and then this one where the line is not going through the middle of the data. The distances between the line and the line where it doesn't go through the data very well is going to give a lot of very high residuals. So they call this ordinary least squares regression. So when you hear that term ordinary least squares regression, you should think linear regression. And there are other methods to estimate for regression equations, and we're not going to talk about them here. The overall model fit is still estimated using R squared in the F test. We talked last week when we had a correlation, a Pearson R correlation, we used little r squared to talk about the percent of shared variance between the independent variable and the dependent variable. And then in multiple regression, we use big R squared, which is a relationship between the independent variables as a unit and the outcome variable or the dependent variable. And as you will see that big R squared is different than any of the individual predictor variables, the correlation between any individual predictor variables. And but when you add in multiple independent variables, sometimes R squared gets a little artificially inflated, and so an adjustment is made, and they call that adjusted R squared. So when you have multiple predictors, it's usually suggested that you interpret adjusted R squared, or at least report adjusted R squared with the regular R squared, so that people know what the adjustment would be for having multiple predictor variables. And we still test the model using an F test. So before we interpret results for regression, we should check assumptions. We still have the same assumptions that we did last week. Our normality assumption, we can check with our Kolmogorov-Smirnov or our QQ plot, or also histograms. You can get kind of an idea if data are normally distributed or not. We should have a continuous outcome variable. Predictor can be any level of measurement. So I think we mentioned this last week, but be aware, we're not going to see examples of it, but any level of measurement. we still have the sample as a random selection from the population, that assumption. Um, Variables need to have a linear relationship, so each independent variable should have a linear relationship with the outcome or dependent variable. Observations are independent. Homoscedasticity, which is like homogeneity variance, but it's for a continuous variable. So at different values of the x variable, we need to see roughly similar distributions of the data around the y variable. A new assumption is we don't want highly correlated predictor variables, and this is called multicollinearity. And usually when you're looking at correlations, you should check those before you run a regression, correlations between the predictor variables, and correlations greater than 0.8 start to become problematic. We're going to learn another tool for looking at multicollinearity called the variance inflation factor, or VIF. And values above 5 are of concern, and above 10 are really problematic, and you should probably do something. And the solution is pretty simple. Since they're highly correlated, they're pretty much covering the same thing, and you should simply pick one of those variables to keep in the equation and let another one go, or just get rid of it. And usually which one you pick is dependent on the theory behind what you're doing, or which one is more important in the context of what you're researching. And then you don't want any quote-unquote bad outliers. And there are several kinds of outliers in regression, and you can see those in the Navarro text. I'm not going to get into them in too much detail, but we have a new tool called Cook's distance. And if you have a value for Cook's distance greater than 1, then you should look at that individual and decide if there's something different about them or a reason why they shouldn't be included in the analysis, because they'll probably impact the numbers that you get in the end. So I left this slide in about heteroscedasticity, and you'll see at lower values of x, the data points are pretty close to the line, but at higher values of x, they start to spread out a lot. So this violates the homoscedasticity assumption. And I went ahead and put these figures from Navarro here in the lecture. A large residual is one that it's along the value of x, and you'll see the y value is way different than many of the others. That's called an outlier. And that is of some concern, but it's not hugely concerned. They don't typically impact the regression too much. This other kind is called a high leverage case, and you'll see that they have a higher x and a higher y than many others, but they still are pretty close to the regression line, and these have minimal impact on the regression results. But you have these cases they called high influence cases, and that's where they're quite a bit different in x and quite a bit different in y, and that they really do impact where the regression line falls. And we're going to see Cook's distance, a value greater than 1. You really need to consider, should that individual be in the analysis or not, and you need to have a good reason to exclude them, but you should go look and see what's going on there that makes them so different from so many of the others. And in regression, we focus on 2 main parts of the analysis. So this we talked about a little bit, but I'm going to stress it a little more here. We're explicitly building and assessing models. We've actually been doing this all semester long. We just haven't called them models, and we're just going to change our language a little bit and say that we're going to build models now. And by a model, we just mean this regression line. And the first thing that we look at is the model overall and the fit of the model. So the next thing we look at is variables in the model and whether the variables in the model play a significant role in the model. And I just want to emphasize this 2-step process to you. As a student, when I realized that we've been doing these null hypothesis significance test steps for all of our tests, we're in essence doing it twice for multiple regression, once with the model and then once for the variables in the model, and that made it a little easier for me to remember. We're going to look at that model, and then we're going to look at the individual variables. And this is the same for all types of regression analyses. So we're learning about multiple regression. Next week, we're going to talk a little about logistic regression because we see that in medicine a lot. And there are other types of regression where you have different characteristics of variables of interest. We're not going to get into them in this course, but they still follow the same pattern. So it's a useful pattern to remember. And we're going to go through the null hypothesis significance test steps for our computer assignment. And the first set we'll go through is for a regression model overall. We still look at the F statistic with our degrees of freedom and our p-value, and our post hoc tests there's a little more that we're going to get into this week about post hoc tests or follow-up analysis. And in regression, you'll see in the Navarro chapter, they call that model checking or regression diagnostics. And we're going to look at some things called residual plots, predictor correlations, and the variance inflation factor, and a new way to measure models called the AIC. That stands for Akagi Information Criterion. And you really don't need to know much about it other than we can get it calculated for us. And the lower the AIC value, the better the model is. And AIC just tries to make a balance between having multiple predictors that help us get a good fit with the model, and yet still having a simple model which is easy to interpret. And so AIC tries to make a balance there. And then we'll see how we look at our adjusted R squared and go on with that. So then we'll run through our NHST steps again, looking at more closely at the variables in the model or the predictors. And we're going to look at a t statistic for each variable, and it's going to give us a significant test for each variable, and we report that with t and the standard error. And then looking at individual cases, we'll look at Cook's distance. So Cook's distance is part of the regression diagnostics. I just kind of moved it over here to individual cases since we're looking at individual variables, but they're all in the same menus. And then we'll look a little bit at selecting the best model. So with multiple regression, we have a little more complexity, and we can actually specify some different models. And it's always a balance between having the simplest model and in more technical terms, they call, or just a bigger word, they call that a parsimonious model. Parsimonious just means a simple model. And the more variables we put in the model, the closer the model actually fit the data. And so you always have a balance there between those two things, between model fit and simplicity. Navarro mentioned that there are some automated methods to do this, and mentioned backward elimination and forward selection. And we're not going to get into that. Those aren't things that are really built into Jamovi right now. And there's some pretty good arguments that you should really be guided by theory and not by an automated process. So Navarro makes a very sound suggestion of go with interpretable models over the best criterion when selecting models. So, and then we're going to look at a way we can compare models, and we can actually get AIC will help us compare models, and then we can set things up in the regression to look at a hypothesis test to see if one model is significantly different than another. Up to this point, we've the hypothesis test we get compares a model to the null model, and now we can actually specify some different models. So we'll see how to do that. It's really quite easy to set up in Jamovi, so I thought let's just show it to you guys because it's there. I had mentioned some issues in the Heavy lecture about Heavy calling unstandardized coefficient the beta values, and that is not the way it is in SPSS. The standardized coefficients are the beta values, and the unstandardized coefficients are the B values. That's the way SPSS does it. Jamovi gets around that by just not using B and beta. They just call it the estimate, and the standardized estimate. Same thing in R. That's another statistical language, and they use estimate and standardized estimate. But I have seen a published paper where somebody called the unstandardized estimates the beta values, which I found very strange because I had been trained differently. But I, just from working with ChatGPT more, ChatGPT used that same convention that the unstandardized estimates are the B's and the standardized estimates are the betas. So I think that is a pretty accepted standard. So I think Heavey made an actual error there. And we looked at the tables on page 188, and that table was listed out differently. And I pointed out to you where that was, and we'll actually see another table on 194 that there's still some mistakes in there about where things are labeled, and we'll compare our results with that. Okay, that's all I have for this lecture. I hope you have a good day and a good week, and we'll talk to you later.